Controlled Environment Plant Production Engineering and Technology Education modules are developed and presented by the Ohio State University, Rutgers, and the University of Arizona with support from USDA and NIFA through their Higher Education Challenge Grant program. This module is developed and presented by Dr. Murad Kasira from University of Arizona and Dr. AJ Boat from Rutgers. This module will introduce psychrometrics and some of the related psychrometric processes. In this module, our educational objectives include defining psychrometrics, learning about thermodynamic properties of moist air, learning about psychrometric chart and how to use it, and we will also look at some of the examples of psychrometric processes. The term psychrometrics derives from the Greek word psychron, means cold, and metron, means of measurement. So in simple definition, psychrometrics is basically the study of moist air properties. However, in engineering terms, psychrometrics is the science involving thermodynamic properties of moist air. Thermodynamic properties of moist air describes the state of a psychrometric process, and when we talk about moist air, we define a mixture of both dry air and water vapor. Here I like to point out that almost all air we encounter is considered moist. That means contains some amount of moisture in the form of water vapor. The overall mixture and each mixture component we encounter in this discussion behaves as ideal gas at the states under consideration. So we consider the system shown in the figure here as the system consists of moist air occupying the volume of V at a mixture pressure of P and the mixture temperature of T. Therefore, the overall mixture is assumed to obey the ideal gas equation of the state, and the ideal gas equation of the state is represented by this equation. In this equation, the variables include the number of moles contained in the mixture, shown by N, the mass of the gas mixture, shown by M, and molecular weight of mixture is shown by capital M. R prime represents the universal gas constant, P is the pressure of gas mixture, V is the gas volume, and the T is the temperature of the gas mixture. Each mixture component, as you can see in this figure, is considered to act as if it exists alone in the volume V and under the mixture pressure of T while applying a part of the pressure in the overall system. This is known as the Dalton law or the Dalton model. So the Dalton law explains that the mixture pressure is the sum of the partial pressures of dry air and partial pressure of the water vapor. Then using the ideal gas equation of state, the partial pressures PA and PV of the dry air and water vapor can be represented by these Neve form of equations. Graphical representations of several important properties of moist air are provided by a handy chart called psychrometric chart. The psychrometric chart these charts are constructed for a certain mixture pressure, so it is important to use the correct chart with the corresponding pressure that is relevant for the process or the system being evaluated. For example, the chart seen in this slide is developed for the sea level and for a barometric pressure of 1 atmosphere, and that's about 101 kilopascal. You can find the psychrometric charts with different units systems. As you can see on this slide, this chart is again for sea level at a barometric pressure of 29.9 inches of mercury, and the chart is presented with imperial units or British units. We will later discuss about how to fix a thermodynamic state by knowing at least two moist air properties and also locating all other thermodynamic properties of moist air by moving around the chart and using different scales as shown on this psychrometric chart. However, we will first review some of the key variables, key definitions and terminologies used in psychrometrics and its related processes. The first set of definitions are related to temperature. Let's first define dry bulb temperature. This is the temperature of air measured by a thermometer that is freely exposed to air but shielded from direct radiation and moisture. It is basically the true air temperature that we feel. The dry bulb temperature are located at the bottom of the psychrometric chart and on the horizontal axis, as you can see on this slide. And the unit of dry bulb temperature is in degrees Celsius because this psychrometric chart is constructed with international unit system. We can also talk about the wet bulb temperature of the moist air. Wet bulb temperature is the temperature that the water, by evaporating into air, can bring the air to saturation adiabatically at the same temperature. In other words, wet bulb temperature is the minimum temperature that the moist air could achieve if enough water was added to achieve saturation, meaning reaching to relative humidity of 100%. Wet bulb temperature is also often used to indicate how much water can be added to air through evaporation process. Wet bulb temperature is also called as the adiabatic saturation temperature. We can locate the wet bulb temperature of the air by following these yellow dashed lines on this particular psychrometric chart, as you can see here, by following the scales as shown on this psychrometric chart. The dew point temperature is defined as the temperature when the saturation is reached to 100% relative humidity, while the moisture content of the air or the humidity ratio of the air stays constant. In other words, dew point temperature is the temperature at which the water will begin to condensate out of moist air. Condensation of the water vapor occurs when the temperature of air is lowered to its dew point temperature. We can achieve dew point temperature by sensible cooling process, which means that the humidity ratio or the absolute humidity of the air remains constant during this process. The dew point temperature can be located on the psychrometric chart using this vertical scale, as you can see on this particular psychrometric chart. So if we know the thermodynamic state, let's assume that we are located at this point, we can move horizontally following the constant humidity ratio lines and locating the dew point temperature of the state using the left-hand side of this vertical scale, again on this particular psychrometric chart. Another way of defining water content of moist air is the absolute humidity or humidity ratio. We can also call a humidity ratio an absolute humidity as specific humidity of the air. And the unit for the humidity ratio is kilograms of water per kilogram of dry air in metric system, or pounds of water per pound of dry air in British unit system. The humidity ratio of the air is actually the actual water content of the air, and it is expressed as the ratio of water vapor, the mass of water vapor, to the total amount of dry air in that mixture. By using the ideal gas equation of the state, we can also derive different forms of equations to represent humidity ratio. If we look at the psychrometric chart, on this particular psychrometric chart, as you can see here, the humidity ratio of the air are represented by this vertical axis here, and so if we know the state for that thermodynamic state, we can move horizontally uh, to locate the humidity ratio on this vertical scale in the psychrometric chart. Another term that we can use to describe the water content of moist air is the relative humidity, and is the one of the simple way of representing the amount of water vapor in the moist air. We can compute relative humidity as the percent water vapor pressure over the saturation vapor pressure, as you can see in this equation. Uh, I like to mention here that the water vapor pressure means water vapor concentration in volume basis. However, partial pressures are commonly used in physics to represent concentration of gases. Therefore, the relative humidity is the ratio of current water vapor concentration in the saturation or the maximum water vapor concentration that the air can hold at that temperature. And if we look at the saturation vapor pressure, it changes with the air temperature. Basically, at about every 10 degrees Celsius increase, the saturation pressure of water vapor doubles. It is important to mention here again that the relative humidity is a relative term, because it depends on the air temperature. The air can hold more moisture at higher temperatures than lower temperatures. Therefore, air at 20 degrees and 40% relative humidity will have lower capacity to hold water than the air at the 40 degrees Celsius and 40% relative humidity. The relative humidity lines are shown by these curved blue colored curves on this psychrometric chart. As you can see, we can locate relative humidity lines from 10% to 20, 30, up to 100%, or the saturation line. So, remembering the effect of air temperature on the capacity of the air to hold moisture, we will recommend another term or variable used to measure moisture content in the air, and that is vapor pressure deficit, and the unit is kilopascal. The vapor pressure deficit is recommended over other forms of defining moisture content in the air, because vapor pressure deficit directly determines the capacity of air to hold more moisture at a given temperature. So the vapor pressure deficit is the difference between saturation vapor pressure and the current vapor pressure at the same dry bulb air temperature. If we look at the psychrometric chart here to find the vapor pressure deficit at a given temperature, let's assume that our thermodynamic state is fixed at this point, so we can locate the current vapor pressure of the air at that thermodynamic state by moving horizontally to the vapor pressure scale here, as you can see. So we can determine that at the current state, and uh, at the same temperature and at the 100% relative humidity, which means the saturation point, we can locate the saturation vapor pressure, again using the vapor pressure scale, and the difference between these 2 points, or between these two pressure levels, defines the vapor pressure deficit. So the vapor pressure deficit again indicates how much more water vapor the air can hold at a given temperature. This table shows the relationship between vapor pressure deficit and relative humidity and air temperature. As you can see here, this column represents the air temperature, and the columns here shows the relative humidity from 0 to 99%, and in the table the vapor pressure deficit is presented at different combinations of air temperature and relative humidity. So you can notice here that we have wide ranges of vapor pressure deficit at lower air temperatures compared to the very narrow range of vapor pressure deficits at higher air temperatures. This is because that the saturation vapor temperature, the saturation vapor pressure increase exponentially as the air temperature is increased. The vapor pressure deficits range that you see here by the pink colored region is actually a good and common range of vapor pressure deficit levels that is good for plant production. Um, um, the growers usually use different ways of representing vapor pressure deficit. Again, one is in terms of using partial pressures with pressure units for vapor pressure deficit, either in millibars or kilopascal or pounds per inch square. Or some of the growers also represent vapor pressure deficit in terms of humidity deficit terms or mass deficit concentration units. Here basically we are looking at the concentration of water vapor in terms of grams of water per volume basis. However, again, we can look at the saturation vapor pressure in terms of mass deficit basis and the vapor pressure in mass deficit basis. The difference again is going to represent the vapor pressure deficit, however, using a different unit and in terms of mass deficit concentration units. And we can convert from vapor pressure deficit in pressure units to mass deficit concentration units, and this relationship, this correlation is basically temperature dependent, as you can see in this equation. Using this table, one can also look at different combinations of humidity deficit or mass deficits in terms of grams of water per volume basis at different combinations of air temperature and relative humidity levels. The specific enthalpy is another thermodynamic property of the moist air, and specific enthalpy is the amount of energy contained in moist air. The enthalpy represents the amount of sensible and latent energy contained in the moist air. If we look at the psychrometric chart, we can find the enthalpy or the specific enthalpy of the thermodynamic state by following these diagonal black lines on the psychrometric chart. Again, remember that the diagonal green dashed lines are used for wet bulb temperature on the psychrometric chart. However, the black diagonal lines are used for finding the enthalpy or specific enthalpy of the moist air. And the unit for specific enthalpy is in terms of kilojoules per kilogram of dry air. The specific volume is the volume of the moist air per unit of dry air basis. This is the volume occupied by both dry air and the water vapor. In other words, this specific volume is the inverse of the air density, and that is shown. The density is shown with kilograms per meter square basis, as opposed to specific volume. The unit for that is meters cubed per kilogram of dry air, or in British unit system, the specific volume is represented by the feet cubes per pound of dry air basis. We can locate the specific volume of the moist air by following or locating the thermodynamic state on these diagonal blue lines, as you can see on the psychrometric chart. So this concludes our discussions for the first part of the psychrometrics and processes module, and we're going to look at some of the example air conditioning processes in the second part of this module. Thank you for listening.